Now let's discuss 8086 memory addressing. We know that 8086 has 20 address lines. That means 2 to the power 20 memory locations. That means 1 megabyte locations can be addressed using the 8086 microprocessor. And that 1 mega locations contains byte at every single location. That means 1 mega locations having 8 bits in each location. That means total 1 megabyte locations can be addressed. We have 2 to the power 20 locations. That means 1 mega locations. And we have data bus of 16-bit. 16-bit data bus. That means at a time we can have 16 bits of data. But as we have a memory location into bytes, that means 8-bit. So to access 16-bit data, we need 2 different cycles. To avoid this problem, we bifurcated the memory into 2 different segments. Let's say this is even segment, even memory location, and this is odd memory location. That means the address starting from odd, it is 0, 0, 0, 0, 1, then 3, then 5, and so on. And for this it is 0, 2, 4, and so on. So if we access these 2 memory chips simultaneously, then in one clock cycle we can have 16 bit of data. That means to access 16 bits we need not to have 2 cycles. We can access the 16 bits at one time if we divide the memory bank into 2 different even and odd addresses segments. Next is generating control signals. To read and write, we have 3 different signals. RD bar is to read, WR bar is to write, and M/IO bar is for input output or memory related operations. So when we want to have a memory read signal, then read bar and memory is connected to a NAND gate. The read bar signal is connected to a NOT gate just to get the same output as 1. So M is 1 and RD bar after passing through an inverter becomes 1. This will be 0, this will be 1. So this 1 into 1, that means output will be 1, and since it's in NAND gate, the output is 0. Active low memory read signal is generated with this method. Similarly, if we want to generate a memory write signal, then write is passed through an inverter. That means if write is 0, then the output of the inverter is 1, and memory related operation, that means it is already 1. So 1 into 1 we'll get 0. So memory write signal is generated. This is the even and odd address bank we have already discussed. 8086. So this is the odd memory segment. This is even address memory segment. We can have 1, 3, 5, and so on, all odd combinations, and this is 0, 2, 4, and so on, and to this is even segments. And since each segment contains 8 bits, so this even address bank is connected to D0 to D7, and odd is connected to D8 to D15. Depending on whether the data is located, 16 bits of data is located at even address or odd address, starting address, we may have 1 or 2 cycles. So in other words, we can say that it requires 1 or 2 cycles depending upon whether the lower order byte of the word, that is of 16 bit, is stored in even or odd memory addresses respectively. Even address bank of memory is connected to lower byte. We have already discussed that even address bank is connected to lower byte of the data, and odd address bank is connected to the higher byte of the data. So if the data 16 bits of data is connected is started from the odd and then even, for example 1 and 2 location pe we have the data, so this 1 must be the lower byte and 2 must be the higher byte. So but in this fashion, this 2 is connected to this lower byte of the data and 1 is connected to the higher byte of the data. So first we need to access the 2, then we need to access 1. That means to access complete 16 bit of data, we need to follow 2 cycles. Now if it is for example the data is written as in 2 and 3 fashion, then this 2 and 3 can both be fetched from the memory at one single cycle, because this 2 must be the lower byte and this 3 must be the higher byte, and this is connected by the even and odd address banks respectively. Here the role of BHE bar and A0 bar is very important, because BHE bar is bus high enable, it's an active low signal, and A0, the address bus A0, will be used to access the 16-bit data or 8-bit data from even bank or from odd bank, depending on the values of BHE and A0. So if BHE and A0 both are 0, that means we are accessing 16-bit of data from both of the memories, bank, even bank as well as odd bank. If it is BHE is 0 and A0 is 1, that means we are accessing the 8-bit of data from the odd memory bank. Similarly, if BHE is 1 and A0 is 0, we are accessing 8-bit of data from the even memory bank. And 1 is not accessed the memory. We are not accessing memory if BHE is 1 and A0 is also 1. Now let's discuss it with the help of an example. For example, we have two 8K into 8 electrically erasable programmable read-only memory. Since it's read-only memory, we have the control signals, the memory read signal. And the problem is given as that the address are starting from FC000 to FFFFF. Now to have an FC000 address, we need to maintain these 20 address lines in this fashion. 0, next 0, next 0, next is C, that means 8 and 4, 12, 0, 0, 12 is C, and this is F. So FC000 is the starting address of the memory, and FFFFF, that is the ending location of the memory. With this address bits, we can have the following diagram of the memory address. 8086 is having A0, A1, A2 and so on up to A13, and A14, A15 up to A19, the total 20 address buses. The 20 address buses are connected in such a way that it is one single chip is of 8K. 8K, that means 2 to the power 3 into 2 power 10. 2 power 10 is K, 2 power 3 is 8. So 8K is 2 power 3 into 2 power 10. That means 13 address lines are needed to have the address locations. So 13 address lines starting from A1 to A13 we have connected to both of these chips. We have not connected A0 because A0 is not used to define the address range. It is basically connected in some logic connections to enable the chip, this one or this second chip, this even bank address bank, and this odd memory bank address bank. And this BHE bus high enable is also connected to the other chip. So A0 is connected to this chip and BHE is connected to this chip. Now take an example in which we have said that BHE is 0 and A0 is 0. So BHE is 0 and A0 is 0. These are all ones. In the previous slide, we have mentioned that these all are 1. FC, that means 1, 1, 1, 1, 1, 1, 1, 1. So these 1 is connected to an AND gate, that means output is 1. This 0, A0, is connected to an inverter, the output is again 1. And as it is passing through an NAND gate, 0 into 0, 1 into 1, that means 1, inverted, that means 0, and is connected to the CE bar. CE bar is nothing but the chip enable signal. It is similar to chip select signal. We want to enable this particular chip. That means at the same time when BHE bar and A0 both are 0, that means even bank memory address memory chip is enabled. Similarly, if we see BHE bar is 0, that means this inverter will convert it into 1, and this another input is the same. That means these higher order address buses will get the output. This 1, that means this is 1, 1 and 1, that means it is 0. This 0, that means chip enable is inverted signal, that means this chip is also enabled. That means the both chips are enabled. Odd bank is connected to D8 to D15, that means higher order data is available, and even bank is connected to the D0 and D7, the lower order data is available. Memory read signal is the output enable signal of the chip. So this memory read is connected to both of these chips in the OE bar, that means output enabled chip of both the chips, output enabled signals of both the chips. Let's take an example of BHE is 0 and A0 is 1. When BHE is 0, that means this will be 0 because this is 1 and this is 1. So this 1 and 1 is 0, that means this is enabled. But what about this even the odd even bank? This is 1, that means after passing through this inverter this will become 0, and when any of the signal is 0 the output is 1. This 1, that means output is 1, is connected to CE bar, and CE bar has to be 0 to enable this particular chip. So when it is 1 it is not enabled, so that means the low order address byte is not connected. Or in other words, we can say that when BHE is 0 and A0 is 1, BHE is 0 and A0 is 1, BHE is 0 and A0 is 1, the 8-bit data is read from the odd memory bank only. This even bank is not connected. Clear? Similarly, we can derive it from BHE is 1 and this is 0. So in that case, this will be disabled and this will be enabled. So we can say that in this fashion, when BHE is 1 and A0 is 0, the data is connected from the even bank only. Odd bank is not connected. Let's take another example in which we have RAM chips, that means random access memory. It can be read and it can be write in both operations can be performed in RAM. So the same 8K into 8 chips, 8K, that means 2 power 13, that means 13 address buses are required to address the 8K chips, and we have two different chips. Address range is given as 00000 to 03FFF. So 00000, that means they all are 0, and 0003FFF, that means this is F, this is F, this is F, this is 3, and this is 0. So the lower order address is 00000 and higher order address is 0003FFF. So to connect this 8K RAM to 8K into 8 RAM chips in this address, we will connect it in this fashion. When A19 to A14, they all are 0, that means to connect it with 1, we need to pass it with an inverter. So after passing through an inverter, this will be 1, and 1 into 1 into 1, all 1. After passing through an AND gate, it will be 1. This 1 into A0. A0 is what? A0 is 0 initially. A0 is 0, that means this is 0 and this is 0. This is 1. This 0 is passing through this inverter, this will become 1. So this will be 1 here and 1 here. So output is 0. Output is 0, that means chip is enabled. Similarly, BHE is 0 initially. As an example, so this after passing through an inverter, this will be 1, this will be 1, that means this is 1, and this 1 is connected to this also. So this 1 and 1 passing through an NAND gate, this will become 0, so this chip is also enabled. So both of the chips are enabled. We say that it is an odd bank because it is connected to a higher order data bus, and it is even bank because it is connected to low order address bus. Similarly, we can see that 13 address buses are required, so we have connected A1 to A13 in both of the chips. Now, as we know that it's a random access memory that we can write and read both, so two different control signals, memory read and memory write, has to be connected to each of the chip. So memory write is connected to write enable, and memory read is connected to output enable. Output enable, that means if we want to read, that means we need to read from the output port, and write enable, that means we are enabling the input so that we can write the memory, right? In this similar fashion, we can have any address combination to have. If we choose A19 to 1 and rest other are 0, that means for that we need to place, for every single 0 we need to place inverter, and for every single 1 we need to replace this inverter by simple line. That means though no inverter is connected. So if it is 1 and all other are 0, that means all other lines are connected to the inverters but not A19. So the address range can be accordingly modified. Thank you.